The Black Hole Firewall, the hardest limit physics has ever found. The horizon wasn't empty, it hissed. Instruments said vacuum, the readout whispered heat. A photon blinked into existence at the edge of nothing, then vanished again like a heartbeat you could almost feel. If this glow is real, the universe has a problem it can't smooth over. Because whatever crosses that line is supposed to be gone, quietly, cleanly, forever. Instead, the boundary talks. To see why that whisper threatened physics, we need to go back to a chalkboard in the 1970s, where a young Stephen Hawking ran headlong into a contradiction. He didn't mean to light the fuse, but that spark still burns. Hawking's spark, how information became a problem. Start with a simple promise physics makes. If you know the present exactly, you can, in principle, recover the past. That's unitarity, quantum mechanics, way of saying the book of reality never loses pages. Meanwhile, general relativity draws black holes like perfect erasers. Pass the event horizon and you're cut off from the universe. Two honest rules, one world. And for a while, they ignored each other. Hawking didn't. He treated empty space as alive with pairs of quantum particles popping in and out. Near a horizon, he realized the pair can be split. One falls in, the other escapes. To distant eyes, the black hole glows. Not with a message, though, with heat. Purely thermal, he calculated. No memory of what fell in. Coffee grounds or a star map, same steam. That was the spark. Here's the stakes in a human heartbeat. Picture a data drive the size of your thumb loaded with a family archive. Photos, letters, a song your grandfather recorded in one take. You toss it toward a supermassive black hole, and the drive crosses the horizon in silence. Decades later, faint Hawking radiation trickles out, indistinguishable from any other. If Hawking's first calculation holds as a final word, those specific memories are gone, not scrambled, erased. That's a world where physics shrugs at lost stories. The action unraveled fast. Jacob Bekenstein had already argued that a black hole carries entropy proportional to its surface area, not volume. That was the first hint the horizon encodes something. Hawking's result added a timer. The black hole evaporates. Enter Don Page with a crucial curve. If information isn't lost, the entropy of the emitted radiation should rise, peak at the Page time, then fall as correlations leak out. A recovery arc baked into the glow. But Hawking's calculation said the radiation stays thermal all the way down. Two curves, one sky. Which one does nature draw? Meanwhile, something else was happening on the quantum side. Entanglement doesn't like to share. Early Hawking quanta flying away are entangled with partners that fell in. Late quanta, if they carry information to fix unitarity, need to be entangled with the early ones too. But a single bit can't be maximally entangled with two independent systems. Monogamy of entanglement is strict. Keep the smooth horizon and you preserve the infalling pairing. Preserve the global purity of the radiation, and those late quanta have to break up with their interior partners to commit to the early crowd. This was the moment everything changed for horizons. The impact landed in 2012 with AMPS, Almary Maroff Polchinski Sully. They pushed the logic. You can't have all three: unitarity, effective field theory outside the horizon, and no drama at the horizon. Drop one. If you refuse to drop unitarity and you trust the outside physics, the horizon can't stay smooth. It becomes a firewall, high-energy quanta right at the boundary, incinerating anything that tries to pass. The equivalence principle takes the hit. Not you'll feel nothing, but you'll feel everything immediately. Get this, the firewall isn't an add-on explosion. It's bookkeeping forced into physics. The entanglement that used to sew the inside and outside into a seamless vacuum has to be cut. Cut the seam, and you expose energy. What looked like empty space turns rough. The quiet doorway becomes a blade. But there was one problem. Nobody can go check. The horizon is a one-way conversation. Even gravitational waves from colossal mergers tell us about the outside ringo, not the microscopic stitchwork at the edge. And critically, there is no direct experimental evidence for or against firewalls. Any tests must be indirect. So the debate went holographic. If gravity in a volume is encoded on a boundary, maybe the information never really disappears inside. It was always on the edge. Add SCFT gave a laboratory. A black hole in the bulk matches a hot quantum system on the boundary that evolves unitarily. That leans toward the page curve. It also hints at something deeper. The interior might be a code, not a place. Meanwhile, theorists tried to save no drama without losing the book. Fuzzballs from string theory replaced the black hole interior with a tangle of strings. No traditional horizon to cross, just structure all the way down. Equals Epper suggests entanglement and wormholes are two faces of one idea. The interior could be connected to the radiation by non-traversable bridges, keeping the horizon calm while information sneaks out in correlations. Soft Hair proposes that subtle, low-energy excitations, charges at the horizon, store details of what fell in, tagging the outgoing radiation with a faint signature. And then came a surprise from the entropy accountants. In 2019, using replica wormholes and quantum extremal surfaces, new calculations reproduced the page curve from semi-classical gravity. Radiation entropy rises, peaks, and falls as if information does come out. That supports unitarity, but it doesn't show you the mechanism in everyday space. It whispers islands, regions that count as part of the radiation's entanglement wedge, even though they lie where we'd call inside. The boundary between in and out blurs in the math. The simplicity of here and there starts to wobble. Microstory, a grad student stares at a plot that dips when it shouldn't. The professor says, "That's the page turn." The student laughs from relief, then pauses. If the curve's right, what does an astronaut feel at the horizon? The room grows quiet. That's where equations run out of comfort. So here's the fork Hawking opened. Keep unitarity and accept that the horizon either isn't smooth or spacetime's bookkeeping is stranger than intuition. Keep no drama, and you're forced to let information die, breaking quantum theory. The glow at the edge isn't the problem, it's the promise. If radiation carries the story back, something fundamental has to give at the limit we called empty. And that limit is where we're headed next. The page curve, when entropy turns around. To see how the glow could keep its promise, we need to track the bookkeeping itself. Entropy isn't a vibe, it's a count. How many microscopic ways the radiation could be, given what we see. Early on, Hawking radiation looks random, so the entropy of that radiation climbs. More quanta, more ways to arrange them. If nothing ties those quanta together, the climb never stops until the black hole is gone. That's Hawking's cliff. A straight line up, then a drop to zero only because there's nothing left to radiate. But that shape hides a crime. It erases the past. Don Page asked a sharper question. What would the entropy do if information isn't destroyed, just scrambled and released? His answer sketched a different arc. Entropy rises at first, as the radiation is genuinely mixed. Then halfway through the evaporation, it hits a peak and starts to fall. Why? Because the later radiation carries correlations with the earlier stuff, knitting the whole into a purer state. It isn't that the photons suddenly develop personalities. It's that the joint pattern matters more than any single piece. The curve turns. That turning point is the page time. Stakes right here. The page time draws a line through every story we tell about black holes. Before it, you could still believe the horizon is quiet, the quanta outside are forgetful, and the interior holds secrets. After it, if unitarity is true, the exterior radiation has to start behaving like a codebook. That forces a choice at the horizon we just set up. Keep the seamless vacuum and you block those correlations. Allow the correlations and you tear the seam. The page curve isn't a doodle, it's an ultimatum. Action moved from thought experiments to controlled arenas. In anti-de Sitter space, where gravity plays on a stage with walls, the holographic dictionary says the boundary quantum system evolves unitarily. Translate that into bulk language and a black hole there must obey the page curve. For years, this felt like a promise without a recipe. Then the recipe appeared in an unexpected place, the entropy formula itself. Semi-classical gravity lets you compute entanglement entropy using replica tricks, copying the system n times and gluing them into a neat geometry, then taking a limit. Most of the time, you assume the copies don't talk. Here's where it gets interesting. In 2019, theorists found new saddle points, geometric contributions where the replicas connect through wormhole-like bridges. Add those, and the entropy calculation flips character after a certain time. The minimal quantum extremal surface that anchors the counting jumps from outside the horizon to a surface that wraps around a chunk of what you'd call the interior. That chunk, an island, counts as part of the radiation's entanglement wedge. The math doesn't care that, in ordinary language, it sits behind the horizon. It's included because it lowers the entropy. Impact, immediate, and unnerving. With those replica wormholes, the radiation's entropy follows the page curve. It rises, peaks, and falls in exactly the way unitarity demands. No hand-waving about future quantum gravity. The result comes from semi-classical gravity plus quantum extremal surfaces. It says the bookkeeping can be consistent without a visible breakdown of physics outside. But there's a cost. The notion of inside and outside isn't absolute. What counts as part of the radiation depends on what you're asking and when you're asking it. Meanwhile, something else was happening in the background conversation. This page-compatible entropy doesn't tell you how to decode the message. It only guarantees that a message is there, hidden in correlations spread across astronomical numbers of quanta. Computational complexity enters like a quiet bouncer. Even if the radiation contains the story, actually extracting it might take longer than the age of the universe. Some argued that if decoding is practically impossible, maybe the paradox was a mirage. But the page curve doesn't care about our patience. It's about what physics allows, not what laptops can handle. A micro story from that moment. A postdoc prints two curves, Hawking's straight rise and the newly computed page curve. On the board, they cross like two roads that refuse to share the same town. They circle the peak in red. If this is right, someone says, the island is real. Another replies, real where? The room laughs. The line between geometry and information just moved under their feet. This was the moment everything sharpened. If the radiation's entropy turns around, the late quanta are tied to something we used to think was inside. Keep no drama, and you're forced to accept that the interior exists only as a code reconstructed from the outside, state by state. Accept a literal interior as an independent place, and the page curve can't turn without breaking entanglement monogamy. The firewall argument didn't vanish, it changed shape. Either the horizon's vacuum structure fails for an infaller, or the interior for that infaller is nothing more than a story consistent with what the outside knows. In the aftermath, proposals split along that seam. equals Epper fans saw the replica wormholes as hints that entanglement really does lay spacetime, with non-traversable bridges bookkeeping the correlations. Fuzzball advocates said, look, the page curve matches because there's structure at the would-be horizon doing the encoding all along. Island enthusiasts stayed austere. Don't picture the island, just use the rule to get the right entropy. 3 accents, 1 claim, the curve turns. What nobody knew at the time was how that turn would feel to a falling astronaut. The math respects unitarity and keeps the outside calm. Does the seam cut for them? Or does the code conjure a smooth interior for as long as nobody tries to decode the radiation? That's the question waiting at the edge, and it leads straight back to the fire. AMPS, the firewall argument lights the fuse. 3 ingredients sit on the table, and AMPS refuses to sweep any of them away. First, unitarity. The global quantum state that includes the black hole and its radiation stays pure. No lost pages. Second, effective field theory outside the horizon. Far from singularities, ordinary quantum field theory works, and local physics doesn't suddenly bend its own rules. Third, no drama. A freely falling observer crosses the horizon and, for a huge black hole, feels vacuum, nothing violent. The original bargain of relativity. The paradox comes from trying to hold all three at once. Start with the late-time photon, the one emitted after the page time. Call it B if unitarity holds. B has to be entangled with the earlier radiation. Call that R, because that's how the total state purifies. Those correlations are the only way the page curve can turn down. But in a smooth vacuum at the horizon, B is also entangled with its interior partner mode, A, the one that fell just behind the horizon when B escaped. That's the local Reindler vacuum, how empty space looks near any horizon. Here's the snag. Quantum entanglement is monogamous. If B is highly entangled with R, it can't also be highly entangled with A. You can't be maximally committed to two different partners. AMPS frames it as a choice. Keep the B, an entanglement, and you preserve no drama for the infaller, but then B can't be correlated enough with R to purify the radiation. The page curve refuses to turn. Unitarity breaks, or cut the B, a tie so that B can knit with R that saves unitarity, keeps the page curve honest and respects effective field theory outside. But cutting the tie changes the local state at the horizon. Instead of the entangled vacuum, you get excitations. Energy, a wall of quanta where there should be calm. That's the firewall. Stakes in human terms. The difference between drifting through a doorway and hitting a blast furnace. If the horizon is smooth, astronauts fall through without noticing anything special. If the correlations have to jump from inside to outside, the interior partner mode A isn't there to cancel the vacuum fluctuations. The infaller doesn't feel quiet space. They meet a bath of high-energy modes. The equivalence principle, the bedrock promise that local free fall erases gravity's tug, takes a direct hit at the place we most wanted it to hold. AMPS pushes further with a thought experiment. Imagine a patient, ridiculously advanced observer far away who collects early Hawking radiation R and performs some insane decoding to distill the particular subsystem RB that purifies the late mode B. Yes, it's astronomically hard, but physics doesn't get to hide behind difficulty. In principle, it's allowed. Now they bring RB close and compare it with B as it emerges. If B is entangled with RB, it can't also be entangled with a behind the horizon. The monogamy conflict is operational. Either the decoding works and no drama fails, or no drama survives and we give up unitarity or outside locality. There's no coast to hide on. The action moves to assumptions. Could effective field theory near the horizon subtly fail, even outside, so that decoders can't actually do the distillation without disturbing the black hole? Some argued complexity makes the decoding effectively impossible, protecting the horizon. AMPS counters. Complexity isn't a law of nature, and the paradox doesn't depend on your computer budget. What if the interior isn't independent at all? Proposals like state dependence and mirror operators say it isn't a separate system. It's encoded non-locally in R, then B being entangled with R doesn't violate monogamy, because A and R aren't independent. AMPS replies, be careful. If interior operators depend on the global state in a way that can't be made consistent for all observers, you risk contradictions when two people try to compare notes, even in principle. Meanwhile, something else was happening in the background. Fuzzballs sidestepped the horizon entirely by replacing it with structure. No smooth vacuum, no B. A pairing to start with, so no firewall. The fire is spread throughout the microstate. equals EPR offers a different escape hatch. Identify entanglement with wormhole geometry so that B's purification with R is a geometric connection, not a competing bond. AMPS doesn't claim those roots are wrong. It says you can't keep all three assumptions unless you pick one of those radical pictures. The comfortable, classical horizon can't coexist with strict unitarity and ordinary outside physics. Impact, immediate and lingering. The community splits along the dropped assumption. Drop unitarity, very few are willing. Drop effective field theory outside. That's a big price where experiments agree with it. Drop no drama, that's the firewall. The argument lights a fuse under every later development. Replica wormholes and entanglement islands show how the page curve can emerge without violating outside physics, but they don't hand a free pass to no drama. If the island means the interior is part of the radiation's entanglement wedge, then for an infaller the interior must be reconstructed from what the outside knows. If that reconstruction is state-dependent and fragile, maybe it holds until someone tries to extract too much from the radiation, and then the seam tears. A microstory captures the mood. A seminar ends with a single sentence on the board. Pick 2, outside locality. Unitarity, no drama. People linger, staring, each quietly crossing out a different word. The fuse Hawking lit now burns at eye level, and nobody gets out of the room without choosing what to save. Fuzzballs, a horizon made of microstructure. While the AMPS fuse burned, string theorists walked up with a different kind of match. They didn't try to keep the horizon smooth, they replaced it. In the Fuzzball proposal, a black hole isn't an empty interior wrapped by a featureless horizon. It's a quantum star made of strings and brains, swollen to roughly the horizon's size. No inside in the classical sense. No silent doorway. Just microstructure all the way out. Here's why that matters. The firewall argument starts by assuming a local vacuum at the horizon so that outgoing modes pair with interior partners. Fuzzballs deny that vacuum from the start. If there's structure at the would-be horizon, there's nothing to pair with behind it. The entanglement that creates the smoothness never forms. You don't have to cut a seam if you never sewed it that way. Action, not slogans. In certain supersymmetric settings where calculations are tractable, string theory can count the exact microstates of a black hole and match the Bekenstein-Hawking entropy. Then, rather than a single geometry with a clean horizon, you get an enormous space of horizon-scale configurations, each a different arrangement of strings and brains. The black hole we draw in textbooks is a coarse average. Pick one microstate, and the geometry caps off before any horizon forms. It's like walking down a tunnel that narrows into intricate latticework, instead of opening into a cavern. Stakes for information are immediate. If the horizon is microstructure, infalling matter doesn't disappear behind an idealized boundary. It interacts with the fuzzball surface, transfers its details into those degrees of freedom, and later radiation can, in principle, reflect those details, non-thermal at fine scales, thermal only in a coarse sense. Unitarity survives without needing replica wormholes to salvage the entropy curve. The mechanism sits where the action is, at the edge. A microstory from this camp. A theorist toggles between two plots, one counting microstates in a protected supersymmetric case, one showing the area law. The numbers line up. They lean back, grin, then frown. Great, but where's the astrophysical black hole? The room goes quiet because that's the challenge. Most fuzzball constructions live in special corners of string theory with high symmetry and BPS protection. Translating that confidence to the messy, rotating, neutral giants in the sky is work still in progress. Meanwhile, something else was happening in the fuzzball narrative, leakage without drama at a distance. The proposal doesn't require violent fireworks for distant observers. Hawking-like radiation still emerges with an almost thermal spectrum but with subtle, state-dependent deviations that carry information. The difference is microscopic and spread across many quanta. To most instruments, it looks like heat. To an ideal decoder with all of it, it's a message. And what about the person who falls? This is where fuzzballs and firewalls part company. Firewalls say the infaller hits high-energy quanta at the horizon because entanglement got cut. Fuzzballs say the infaller meets structure because there was never a vacuum there. The energy scale of that encounter depends on the microstate and the infaller's probe. Some advocates argue that for coarse, low-energy probes, certain correlators reproduce fuzzball complementarity, a kind of effective smoothness over short times and distances, enough to mimic no drama for a while. But for fine-grained questions, the structure shows through. It isn't free fall forever. It's a soft landing on a quantum mattress that eventually pushes back. Critics push on two fronts. First, Can fuzzballs reproduce the astrophysical signals we actually measure, ringdoms, shadows, accretion disk spectra, without obvious deviations? If the surface sits where the horizon would be, echoes or reflections might appear in gravitational waves. So far, searches haven't found robust, widely accepted echo signatures tied to horizon-scale surfaces. Second, even if the microstates exist in protected models, do generic, non-supersymmetric black holes share the same horizonless cap? This is an open door, not a settled hallway. Impact on the big argument is clear. Fuzzballs drop no drama in the strict sense at the horizon, but keep outside effective field theory intact and save unitarity with a tangible mechanism. They don't need an island prescription to lower entropy. The degrees of freedom at the edge write the page curve by hand. If they're right, the firewall isn't a sudden wall of energy. It's the permanent fact that the horizon was never empty. The boundary always talked because the boundary was the system. There's a human beat here. A young researcher stares at a sketch of a capped-off throat and whispers, "So the inside is a myth." Their advisor shrugs. A useful myth until you ask too much of it. The promise of fuzzballs is blunt. Make the microstates concrete and you don't need paradox to keep score. But to carry that promise from chalkboard worlds to the black holes we photograph, the microstructure has to survive reality's test. That's the next fight. Equals Epper and soft hair, keeping the horizon smooth. While fuzzballs rewrote the edge's structure, another camp tried to keep the doorway calm without sacrificing the book. Their bet wasn't to add matter at the horizon, but to change what we think space and entanglement mean. Start with a strange sentence that took years to sound less crazy. Entanglement is geometry. ER equals EPR. Here's the claim in plain terms. Take two quantum systems that are maximally entangled, call them twins. From far away, they're just correlated. From the right gravitational angle, those correlations look like a non-traversable wormhole connecting them, an Einstein-Rosen bridge. You can't fly through it. You can't send a message. But as a bookkeeping device for how pieces of a pure state are tied together, the bridge is the map. The more entanglement, the thicker the bridge. The less entanglement, the thinner it gets. Cut the entanglement and the bridge pinches off. Why does that matter at a horizon? AMPS forced late radiation B to be entangled with early radiation R if unitarity holds. Equals Epper says that entanglement is a kind of geometric link. So B's purification with R can be drawn as a thin web of non-traversable bridges from the black hole to the radiation bath. No one walks across, but the pattern changes the interior's bookkeeping. Instead of B needing a separate, independent partner A behind the horizon, its partner is encoded across R with the bridge tracking that tie. You don't violate monogamy because A, defined carefully, isn't independent of R. The interior isn't a standalone warehouse. It's a reconstruction from the outside entanglement structure. Action, where this becomes more than a metaphor, shows up in toy models and holography. In add SCFT, cooling or heating the boundary theory changes the bulk geometry. Entanglement wedges, the regions of the bulk reconstructible from a given boundary region, grow and shrink as you change which degrees of freedom you hold. Move enough information into R, and the wedge that belongs to the radiation can include an island behind the horizon. That's the island rule we met earlier, now wearing equals Epper badge. The bridges don't let you send a signal, but they shift what counts as inside for the purpose of reconstruction. Smoothness for the infaller becomes a property of whether the right entanglement is intact, not a fixed feature of a place. Stakes for human falling in. If nobody has tried to violently distill R into a form that singles out B's purification, the entanglement web remains unbroken. The local state near the horizon still looks like vacuum, no furnace. If in principle, a godlike decoder outside assembles RB and drags it back, the web structure changes relative to that observer. Some versions of the proposal say this can destabilize the interior for the infaller, replacing smoothness with excitations. Smoothness isn't a promise, It's a contingent truce that holds as long as certain operations aren't performed. The firewall becomes a conditional outcome of meddling, not the default. Meanwhile, a softer idea arrived at the edge: soft hair. Hawking, Perry, and Strominger argued that black holes aren't bald after all. They carry an infinite set of subtle charges associated with asymptotic symmetries, BMS supertranslations, and their cousins. These soft modes live at zero energy in the limit, but record how fields cross the horizon. Think of them as a ledger etched into the boundary's fabric. Infalling matter shifts the soft charges. Outgoing radiation can, in principle, be stamped by those shifts. Here's why it matters. If the horizon hosts soft hair, then even a nearly thermal flux can carry imprints, tiny angle-dependent correlations or phase relationships that depend on what fell in. No need for violent departures from effective field theory. No need to break no drama. The information isn't in each photon's color. It's in how the whole orchestra plays over time. Soft hair doesn't by itself compute the page curve or solve monogamy, but it widens the menu of degrees of freedom at the edge that can help. Combined with the equals Epper map, the story reads: the boundary keeps records, and the geometry of entanglement knows how to read them. Critics ask for receipts. Can soft hair alone encode enough detail to match the Bekenstein-Hawking entropy, or does it just scratch the surface? Most agree it's not the whole answer. Can equals Epper be made precise beyond slogans? In certain dualities and quantum error-correcting code models, yes. Interior operators can be reconstructed from different boundary regions state-dependently without contradiction, as long as you respect who can compare notes. Push too far and you risk paradoxes. Stay within the code's rules and no drama survives for ordinary infall. A micro-story closes the loop. Two colleagues argue over coffee. So the interior is a code glued together by entanglement and the hair writes what happened. One nods. Then why did we ever think there was a place to fall into? The other smiles. Because for most questions, the code draws a place, until you ask the one that breaks it. Islands and the modern page curve. The interior moves. To see how the code draws a place, and then quietly moves its walls, we follow the islands. Not palm trees, entanglement islands. They enter as a rule for counting what the radiation knows. You fix a time, pick the radiation far away and ask, what bulk region can that radiation reconstruct if you had the ideal decoder? Early on, the answer hugs the outside. Later, after the page time, something flips. The minimal quantum extremal surface slips behind the horizon, and the entanglement wedge of the radiation suddenly includes a chunk that classical intuition called inside. That chunk is the island. Why would bookkeeping reach past a horizon? Because the entropy wants to be as small as the rules allow. The generalized entropy area over 4G plus the quantum field's entropy competes across surfaces. Before the page time, the outside surface wins. After, a surface that wraps the interior lowers the count. When you include it, the radiation's entropy turns down, matching the page curve. It isn't a trick. It's the same logic you use to decide which cut gives the smallest boundary for a soap film, now with quantum terms added. The film jumps to a new frame. Stakes for reality. If the island sits in the radiation's wedge, then what is inside the black hole depends on who holds which quantum. Give me the early radiation and I can, in principle, reconstruct operators that act in the island. Take that radiation away, and the interior I can access shrinks. Interior isn't a fixed room. It's a reconstruction privilege that shifts with entanglement. That sounds abstract until you put a human next to it. An astronaut falling in feels smooth vacuum if the outside world hasn't done the kind of distillation that yanks the relevant entanglement out of reach. If someone has, the reconstruction can fail for them. The interior moves because the code's ownership moved. Action where this gets teeth shows up in solvable models. In two-dimensional gravity coupled to baths, Teitelbaum setups that you can actually compute, Replica wormholes appear in the path integral once the radiation region grows. The dominant saddle that sets the entropy connects copies in just the right way to include an island. You don't draw a firewall, you sum geometries. The page time emerges from parameters you control: coupling, temperature, size of the bath. You can watch the minimal surface jump in a plot and know you've crossed from no island to island with a change in dominance, not a decree. Meanwhile, something else is happening in the language of quantum error correction. In holography, bulk operators are redundantly encoded in boundary degrees of freedom. One boundary region might reconstruct a point in the bulk. A different region can reconstruct the same point with a different map. This redundancy is what protects the interior from small errors. Islands extend that logic to the radiation. The decoding key that includes the island isn't any single photon. It's the right global slice of the radiation Hilbert space. That's why the information can be out there without any one detector seeing it. The code spreads it so thin you need almost everything to call it back. Impact, immediate for the paradox. Monogamy starts to look less like a brick wall and more like a ledger's constraint. If the island is part of the radiation's wedge, then the late mode B can be entangled with the interior partner A, and still be entangled with the early radiation R because, from the code's perspective, A isn't independent of R after the page time. They're two reconstructions of the same underlying degrees of freedom. You didn't let B marry two partners. You realized there was one partner seen in two mirrors. That reframes the AMPS fork without magic. You keep unitarity and effective outside physics, and you keep smoothness as long as nobody performs operations that invalidate the reconstruction for the infallible. A microstory lands the point. A grad student writes interior equals reconstruction on a board, then erases interior and writes access. The professor nods. Good. Now ask who has it, they list. The radiation holder with the right key, the near-horizon lab, the infaller. 3 perspectives, 3 wedges, 1 global state. The room goes quiet because the place we thought was a place is now a view. There's a cost baked in. The island rule is a statement about entropy, not a blueprint for a device. It tells you that decoding is possible in principle and how the count stays honest. It doesn't hand you the algorithm to reconstruct an interior diary from trillions of quanta. Complexity still stands at the door, arms crossed. But principle matters. Physics won't let you lose the diary. It also won't let you put it on a single shelf. And the horizon. It keeps whispering, but the whisper's meaning changed. The boundary talks because the boundary is where the code lives. The interior moves with the code, and our comfort with here and there has to move with it. The page curve isn't just a plot, it's a map of that motion. Observational hints and hard limits. While all this math moved walls, telescopes kept staring at the edge of darkness, asking a simple question. Does any of it leave a mark we can see? The answer so far is careful. We see horizons behave like horizons. We don't see fire, but the way we don't see it matters. Start with the loudest events in gravity, the mergers that shake spacetime. LIGO and Virgo catch black holes spiraling together and ringing down like struck bells. Those ringtones match general relativity's predictions for smooth horizons frighteningly well. If there were a hard surface just outside, you might expect echoes, late-time faint repetitions as waves bounce between the surface and the photon sphere. Teams have hunted for those whispers in data, sometimes claiming hints, then walking them back as analysis improves. As of now, no robust, community-accepted echo signature stands. That doesn't prove the horizon is empty. It sets a bar. If there's structure, it either sits so close to the horizon that echoes are vanishingly delayed and damped, or it doesn't reflect the way a wall would. Meanwhile, something else was happening at radio wavelengths. The Event Horizon Telescope took portraits of M87 and SGR-A, showing a ring of emission shaped by gravity lensing light near the edge. Those images agree with a spacetime that bends paths exactly as a classical black hole would. No bright surface glare where a solid object would heat up under infalling matter. That constrains horizon-scale surfaces that radiate like normal matter. It doesn't veto subtle hair or code-like structure. It just tells you the boundary, if it's there, stays quiet to crude probes. Gravitational wave memory arrived as a slower clue. After a burst passes, spacetime doesn't quite snap back. It keeps a tiny offset, a permanent record. Simulations include that now, and detectors chase it at the edge of sensitivity. Memory doesn't test firewalls directly, but it tests the precision of our models. The closer those models hold, the less room there is for wild departures outside the horizon. The paradox has to live at scales our instruments don't yet touch. Microstory. A data analyst at 3 in the morning scrolls a residual plot from a merger. No echo bump. They sigh, then smile anyway. Clean ringdom, they mutter. Across the hall, a theorist updates a slide. If echoes exist, their amplitude must be below x. The distance between those two sentences is where progress hides. You might ask about Hawking radiation, the glow that started this. For astrophysical black holes, it's hopelessly cold. A solar mass black hole sits at a temperature of nanokelvins. Supermassive ones are colder still. The cosmic microwave background is a bright oven by comparison. No telescope will resolve that thermal trickle. That's a hard limit on direct tests of the evaporation story and the page curve in the sky. If we ever see Hawking like a mission, it will be in analogs, fluids, optical media, clever lab setups that mimic horizons for sound or light. Those analog systems have reported stimulated and spontaneous radiation with thermal characteristics. They are suggestive, not decisive. They test the kinematics of horizons, not quantum gravity's deep bookkeeping, and they do not provide direct evidence for or against firewalls. What about naked firewalls? Effects outside the horizon we could catch. Speculative ideas propose quantum fluctuations that push energetic layers outward, or near-horizon atmospheres that modify accretion spectra. So far, X-ray and infrared observations fit models with smooth horizons and messy disks. No sharp excess screams fire. That again narrows parameters. If there's drama, it hides behind the line or wears a mask our current models also wear. Complexity enters as a practical wall. Even if the radiation encodes a message, decoding demands almost all of it and computational effort that scales beyond any feasible machine. Observationally, that means correlations that prove unitarity can't be extracted by piecemeal, local measurements. You need a census of almost everything emitted over eons. The universe doesn't hand those to us. Still, there are plays left. Future detectors, Einstein telescope, cosmic explorer, will read ringtones with finer ears, pushing echo limits down another order of magnitude. Space-based LISA will hear supermassive mergers, where the geometry lingers and tiny deviations have more time to matter. EHT's next-generation baselines will sharpen the ring, probing closer to the photon orbit. If any horizon-scale structure reflects, delays, or slightly brightens, those instruments are our best shot. And then there's the quiet revolution in theory-driven data analysis. Machine learning trained on millions of simulated black holes now pulls spin and inclination from interferometric fuzz. That same approach can hunt for patterns too faint for traditional templates, correlations that would hint at soft hair or horizon microstructure without calling them by name. No fireworks, just better ears. Hard limits remain like guardrails. Causality blocks direct peaks behind the horizon. Hawking radiation is too cold to catch. Decoding demands an impossible census. Within those rails, we nibble at the edge, tightening what no drama can mean and how much structure can hide. The boundary still whispers. Our job is to learn which whispers are physics and which are our own machines. The next act turns from what we can't see to what the horizon itself might be telling us about the limits of reality. Limits not of instruments, but of meaning. Simulations, machines, and the Event Horizon Lab. While telescopes press against hard limits, another kind of observatory spun up in basements and supercomputers. Not mirrors, models. Simulations turn the horizon into a lab you can pause, rewind, and instrument any way you want, asking questions nature won't let us. They don't break causality, they work around it, one equation at a time. Start with the workhorses, numerical relativity. Teams like SXS run Einstein's equations at full blast, evolving binary black holes until they collide and settle. These aren't cartoons. They're catalogs, thousands of runs with different masses and spins, now even including gravitational wave memory, the permanent offset left after the storm. The payoff isn't just waveforms for LIGO. It's a stress test of no drama outside. If exterior physics had to bend in obvious ways to save unitarity, the ringdoms would drift. They don't. So whatever the fix is, it hides at scales these codes can bracket but not resolve. Meanwhile, something else was happening with light. Ray tracing pipelines push photons past the photon sphere and into the maw, mapping what an accretion flow would paint on our detectors. NASA's latest visualizations aren't just pretty, they're controlled experiments. Change the spin, tilt the disk, alter the plasma. Then ask, if the boundary carries soft hair or subtle structure, how would that imprint the halo? The answer so far is boring in the best way. The classical lens wins in broad strokes. Any extra story rides in small correlations, not in bright scars. Micro story from that world. A grad student toggles a checkbox, include returning radiation. The ring thickens, shifts. They mark the shift, then sigh. Degenerate with disk turbulence. Translation. Even if the horizon writes a signature, the storm in front of it can hide the ink. Then there's the code that treats gravity like a heat engine. Black holes with pressure and volume, phase diagrams, efficiencies. It sounds like metaphor until you remember Bekenstein and Hawking put entropy and temperature on black holes for a reason. Thermodynamic models probe how information might flow in a system that radiates almost thermally but not quite. Swap a piston for a horizon and ask how much structure you need at the edge to bias the steam. You don't get page curves from these engines, but you do get intuition. If the boundary has microstates that interact with infalling matter, tiny departures from perfect thermality are natural, not exotic. The machine side isn't just physics running forward. It's also inference running backward. The Event Horizon Telescope's raw data is a noisy mess. You can't reconstruct an image without assumptions. So teams trained Bayesian neural nets on millions of synthetic black hole scenes, then asked the nets to pull spin and orientation from real visibilities. That's not guessing. It's compressing prior knowledge into a fast filter. The same trick can hunt for weak, non-trivial patterns, minute phase correlations, asymmetries that stay stable across epochs. That could be a fingerprint of near-horizon structure or soft charges. No fireworks in a single pixel, a whisper in the statistics across the ring. Stakes for the paradox show up in a different class of simulations. Toy universes built to be solvable. Two-dimensional gravity coupled to baths where replica wormholes actually dominate. You press run, and the entropy of radiation rises, peaks, and falls. The page curve appears because the code includes islands automatically when the saddle flips. It's not reality's full texture, but the moral is loud. You don't need to violate outside physics to keep Unitarity's book balanced. Geometry in the path integral does the accounting. A micro story from those runs. The plot turns down on schedule. Someone claps, then someone else leans in. Where's the algorithm? Silence. The curve tells you the message is out there. It doesn't hand you the decoding key. Meanwhile, the community learned to translate these models into error-correcting code language. Bulk operators are redundantly encoded on boundaries. Islands extend that redundancy to radiation. Simulations of simple codes show how an interior diary can be reconstructible from one share of the system, and not from another, with smoothness for an infaller tide to which share remains unmeasured. It reframes no drama as a conditional promise. Don't touch certain correlations outside, and the inside stays coherent for you. Here, S where simulations and machines meet reality, forecasting tests. Next-gen ground detectors will hear cleaner ringtones. Lisa will linger on supermassive songs. Synthetic catalogs already inject faint echo-like features at amplitudes far below today's limits to see if analysis pipelines cough. Most cough. Teams fix them. EHT's longer baselines will push closer to the photon orbit. Mock data trains algorithms to spot patterns that disk physics can't fake. We're not building a telescope that sees through horizons. We're building a discipline that corner-checks every assumption the paradox depends on. Every clean ringtone narrows the room. Every robust null result trims the wiggle. And every simulated page turn reminds us the bookkeeping can work without letting anyone through the door. The information horizon beyond black holes. We've been staring at horizons as if they only live around black holes. But the deeper we go, the more that information boundary shows up everywhere we try to push meaning past measurement. The limit isn't a ring in space, it's a rule that follows us. Start with the oldest horizon we all share, the cosmic one. The universe has only been transmitting light for 13.8 billion years, stretched by expansion. There's a sphere beyond which signals simply haven't had time to reach us, the particle horizon. Another sits closer in spirit to our paradox, the cosmological event horizon in an accelerating universe. Anything beyond it can never influence us, no matter how long we wait. That's not a black hole, yet it behaves like one in the math. De Sitter space, the model for a universe with constant dark energy, comes with a horizon temperature and an entropy proportional to its area. A horizon, a temperature, and area law. The bookkeeping rhymes. If horizons count states, then even empty cosmic space keeps a secret ledger on its edge. Stakes emerge quickly. If De Sitter space has entropy, it has a maximum number of distinguishable states tied to the horizon's area. That hints at a hard cap on how much information a patch of our universe can hold or process. Cosmology turns into a storage problem. You can't just pour in more detail forever. The surface area says when to stop. The same hunch that Einstein used for black holes, no more bits than area in Planck units, looks like a general rule. Meanwhile, something else was happening in laboratories that never touched a telescope. Quantum mechanics draws its own horizons in the sand. The no-cloning theorem says you can't copy an arbitrary quantum state. The uncertainty principle blocks precise, simultaneous knowledge of complementary properties. Quantum speed limits bound how fast states can evolve. Each is an information horizon, a line that turns in principle into no. There's no firewall here, but the logic is the same. Rules that keep stories from being duplicated or pulled out faster than the theory allows. When you ask too much of the universe's memory, it answers with limits, not hacks. Then there's complexity, which walks in like a quiet law enforcement officer. Even when the message exists, encoded in Hawking radiation, tucked into correlations across a galaxy's worth of photons, extracting it might require operations whose time cost grows faster than the age of the cosmos. This isn't taste, it's scaling. In holography, people tie interior volume or certain gravitational actions to computational complexity in the boundary theory. The picture that emerges is odd but consistent. As black holes age, their interior grows in a way that mirrors the growth of the complexity required to reconstruct fine-grained details. You can keep the page, but turning it might take longer than you have pages left. A micro-story lands the point. Two friends argue over a hard drive buried in a mountain. One says, "It's safe, nobody knows the password." The other says, "It's safe because 1,000,000,000,000 years isn't enough to try every password." Both are right for different reasons. Physics uses both locks. Some doors are sealed by principle, others by time. Information horizons also show up in signals, not just storage. When spacetime stretches, it redshifts light, draining energy from messages until they fade into the noise. At some distance, a message is there in principle, but buried under thermal backgrounds you can't cool away. In expanding universes with horizons, even a perfect receiver can't beat that fade. The channel's capacity hits zero. You didn't lose the story, the medium refused to carry it. And while we're here, note the area law's reach. In many quantum systems, spin chains, cold atoms, the entanglement entropy of a region scales with its boundary, not its volume, when the state is gapped or ground-like. That's a hint that less interior than you'd think is a common theme. Holography takes that nudge and turns it into a map. Bulk geometry emerges from entanglement patterns across boundaries. If that's the rule, then every time we draw a border and talk about the inside, we're already writing a code. The horizon isn't out there, it's in how we split the world. Stakes human-sized. Meaning has a map limit. You can hide a diary in correlations, but you can't make it accessible to everyone everywhere at once. You can build bigger telescopes and colder detectors, but you can't beat an event horizon with patience. You can scramble a quantum state and promise that, with the right algorithm, it's recoverable, but the algorithm might be longer than civilization. We don't get to decide which limits are practical and which are absolute. The theory draws both. Meanwhile, the soft hair idea broadens the choir. If asymptotic symmetries act like a record-keeping device at boundaries, then every boundary keeps records. Future null infinity for outgoing radiation, cosmological horizons for the universe's own ledger. That doesn't hand you a decoding device. It does say, don't throw away the edge remembers. Here's where all of this loops back to our fire. AMPS framed a local crisis at a black hole's door. Islands, equals EPR, and Fuzzballs offered different ways to keep the book straight. But the pressure they exposed isn't local to that door. It's a general fact about how physics guards information, with surfaces, with entanglement, with complexity, and with horizons that move depending on who holds what. The firewall, if it exists, is one kind of warning label. The bigger label says, the universe enforces its meanings at boundaries. We like to think knowledge grows by marching forward. The horizon lesson is that knowledge grows by negotiating edges. Black holes made that negotiation violent. Cosmology made it vast. Quantum theory made it precise. In every case, the message is the same. There's a line where what is and what can be known part ways, and the line has teeth. Complexity, decoding, and the practical firewall. We've been careful to separate principle from practice. The page curve says the message is out there. Islands say the interior can be reconstructed from the outside, given the right share of radiation. equals EPR sketches how entanglement can stand in for geometry. None of that tells you how a real being does the trick. This is where complexity walks on stage and draws a second horizon, when you can't cross by willpower. Start with a simple challenge. You're handed a box of Hawking photons collected over eons, a jumble of frequencies and phases so messy it might as well be static. Somewhere in there is the diary of what fell in, the data drive, the star map, the song. Unitarity promises it survived as correlations. Your task is to read it. In quantum terms, you must apply a unitary that unscrambles an astronomical code. How hard is that? Not hard like buy a faster computer. Hard like the circuit depth grows exponentially with the black hole's entropy. The number of gates you need scales like the number of microstates, and that number is exp area/4g. That's a mountain that grows faster than your ladder. Here's the stakes in a heartbeat. If decoding takes longer than the age of the universe, then for any mortal agent the information might as well be gone. Not erased, banished behind a practical horizon. That's the practical firewall. You don't hit flames, you hit time. The universe says, yes, the story exists, and then it bills you more steps than reality can supply. The result feels like loss, even when the math says preservation. Action, where this gets teeth, shows up in toy models you can solve. Think of Hayden Preskill. Toss a diary into an old black hole that's already past its page time. In principle, after a scrambling time of order, the black hole's radius times a log of its entropy. The information about the diary starts coming out. But the decoding map that extracts it is wildly complex. You need almost all the radiation and a circuit that effectively inverts the black hole's scrambling unitary. That's like asking for the exact reverse of chaos. You can write the inverse down as a matrix. You can't implement it without eating lifetimes. Meanwhile, something else was happening in holography. People tied interior growth to the growth of computational complexity in the boundary theory. Complexity equals volume, or complexity equals action. As the black hole interior grows at late times, the minimal circuit that prepares the boundary state also grows. You can keep a state pure forever, but the effort to rewind it keeps climbing. That picture reframes the interior as the cost of remembering. The longer you wait, the deeper the debt. A microstory lands the mood. A postdoc sets up a small-scale decoding experiment on a quantum processor. 5 qubits pretend to be a baby black hole. 1 qubit is the diary. Random circuits scramble, then they try to invert. On the screen, fidelity peaks for shallow circuits, then collapses as noise and depth pile up. We know the algorithm, they say, and we still can't get it back. The lab laughs, not with despair, but with recognition. The wall isn't ignorance, it's cost. Critics use this wall as a shield for no drama. If nobody can decode R into a form that threatens the interior before the astronaut crosses the horizon, then the monogamy conflict never becomes operational. You can sketch AMPS's distillation device on a board, but you can't build it within the light cone that matters. From the infaller's perspective, the entanglement that sews the vacuum stays intact. The bridge doesn't snap because no one yanked on it in time. Smoothness survives as a practical guarantee. AMPS pushes back. Complexity isn't a fundamental law. Physics can't hide contradictions behind too hard. The counter is subtle. Complexity isn't a loophole. It's a second kind of law, evidenced by everything we've learned about quantum circuits, chaos, and error correction. You don't need to promote it to a principle to respect its teeth. The universe is full of processes that are allowed in principle and impossible in practice. No cloning forbids copying. Complexity forbids efficient unscrambling. Meanwhile, error-correcting code language ties the knot. Interior operators are redundantly encoded. You need the right threshold of shares to reconstruct them without corruption. That threshold acts like a key length. Small local measurements can't see the diary. Partial grabs of radiation can't pull on the right degrees of freedom. Only a global, high-complexity operation recovers the story, and performing it can, depending on the setup, change which wedge you control, degrading the interior you were trying to access. Try to open the vault and you move the room. Stakes human-sized again. Meaning doesn't only depend on what exists, it depends on what can be done. The practical firewall says the universe enforces kindness at horizons not with mercy but with scaling. Astronauts cross in peace because nobody can reorganize the outside fast enough to ruin it for them. The story escapes slowly, braided into noise, waiting for a decoder that will never be built. Here's the turn that matters for our finale. Principle saved the book. Complexity saved the experience. Between them sits a rule we keep running into. Reality isn't just about what's true, it's about what's reachable. The horizon writes both limits at once, and when those limits collide, that's where the edge of meaning lies. Black Hole Complementarity Revisited. Before Firewalls, complementarity was the truce that let everyone keep their favorite principle without open conflict. It said two stories could both be true because nobody could compare notes. From far away, information never really crosses the horizon. It piles up on a stretched membrane just outside, gets scrambled, thermalized, and eventually radiated back out. From the infaller's frame, nothing special happens at the horizon. They fall through smooth vacuum. No contradictions, because the observers can't meet to check. Here's the original picture in simple strokes. Outside, imagine a hot, plank-thick, stretched horizon living one hair above the true one. It's a physical membrane with temperature, viscosity, and an enormous number of degrees of freedom. Anything you drop toward the black hole excites that membrane where it gets rapidly scrambled. Unitarity lives there. The membrane absorbs and later re-emits information as slight, state-dependent deviations in Hawking flux. Inside, effective field theory and the equivalence principle describe a quiet crossing. The secret sauce was no double counting. You're not allowed to treat the exterior copy on the membrane and the interior diary as two independent pieces. Pick an observer, pick a description. Stakes right where AMPS cut. Complementarity was built to dodge monogamy trouble by denying simultaneous operational access to both sides. If no observer can hold the early radiation R and also meet the late mode B at the horizon, you never have to confront B's loyalty. The page curve can turn because the exterior membrane returns information. The infaller still feels calm because the local vacuum sewing B to its interior partner, A, isn't threatened by outside decoding that hasn't happened in their light cone. But AMPS pressed an uncomfortable what if. Suppose an insanely advanced observer collects enough early radiation to distill the purifying subsystem RB, then hovers near the black hole and measures B as it emerges. In principle, their worldline can do both. Complementarity's shield looked thinner once. In principle, operations were on the table. If B is entangled with RB for unitarity, it can't also be entangled with A for no drama. Complementarity had to answer more precisely. Not just no one can compare notes, but no consistent quantum description exists that lets both be independent. Action moved to sharpening the rule. One upgrade came from quantum error correction. Don't think of inside and stretched horizon as two warehouses with duplicated goods. Think of them as two reconstructions of the same encoded data. Interior operators are mirror reconstructions that different observers can access depending on what Hilbert space they control. For the infaller, who hasn't interacted with or decoded R, the relevant code subspace realizes a smooth interior with B paired to A for the exterior decoder with RB in hand. The reconstruction changes. The degrees of freedom that would have been labeled A are now spread across R. There isn't double entanglement. There are two frames carving the code differently. Meanwhile, something else was happening that strengthened the story. Islands and entanglement wedges gave complementarity a geometry. After the page time, the wedge of the radiation includes an island that we would have called inside. That means, to an agent who holds sufficient R, interior observables are reconstructible from outside data. To the infaller, who doesn't, they're coded locally behind the horizon. Complementarity stops being a slogan and becomes a statement about which wedge an observer's algebra can act on without contradiction. There's a cost, and it's subtle: state dependence. The precise map that reconstructs interior operators can depend on the global state, and on which exterior degrees of freedom remain unmeasured. Critics worry that this invites paradox if two observers try to use different reconstructions on overlapping regions. The reply is operational. Quantum mechanics already polices incompatible measurements. If an outside agent actually performs the monstrous distillation that targets B's purifier, they change the code space relevant to the infaller's interior. In trying to force a contradiction, they move the furniture. Complementarity doesn't break, the setup does. Microstory from a chalkboard. Someone writes, "No single observer can witness cloning." Another adds, "And if you try, you spoil one copy." Laughter, then a nod. That's the heart of the upgraded truce. So where does this leave Firewalls? Complementarity doesn't assert a cushion of mystery. It specifies when smoothness is guaranteed. If outside physics remains ordinary, if no one has performed global, high-complexity operations on R within the light cone that matters, the infaller's code stays intact, and the horizon looks like vacuum. If an operation strong enough to distill RB is actually executed and brought to the edge, the reconstruction for that agent no longer includes the same interior pairing. In that frame, no drama can fail. The firewall becomes conditional, not universal. Impact right now. Complementarity survives by becoming precise. It's not two truths, it's one code with different valid reconstructions. It keeps unitarity with the stretched horizons ledger, keeps outside effective field theory, and protects the infaller's calm under clear, enforceable conditions. The horizon isn't a place that's smooth or burning. It's a promise that depends on who's asking and what they've done. The human edge: risk, curiosity, and crossing boundaries. Get this, the first person to step off a cliff with a silk canopy wasn't trying to beat gravity. They were trying to learn what gravity allows. That's the impulse that keeps showing up at horizons. We don't tempt edges to break them. We go because edges tell the truth faster. A physicist stares at a blank board and writes 3 words: unitarity, locality, smoothness. Then they cross one out and feel a knot in their stomach. It isn't a math problem anymore. It's a value judgment. Which promise do you keep? The choice lands like a personal risk, because choosing wrong wastes years you don't get back. Still, they choose because not choosing is the quietest way to be wrong. Meanwhile, an experimentalist tapes a checklist to a cryostat. The detector won't hear Hawking radiation, but it might shave a decimal off ringed-on uncertainties. That's not glamorous. It's risk measured in midnight hours and grant renewals. The bet is simple. If reality hides its secrets at horizons, then relentless precision at the edge will either catch a crack or prove how strong the seam is. Here's where it gets human-shaped. Astronauts talk about the Kármán line like a rite of passage. There's nothing there, no tape across the sky. But your body knows when the blue fades to black and the world curves below you. The black hole horizon is like that, scaled beyond comprehension. We can't cross it, but we built a culture around the act of approaching it, mathematically, instrumentally, imaginatively, again and again, knowing each approach might show us our own limits more than nature's. Curiosity isn't free. The firewall argument forces us to admit we can weaponize knowledge against experience. Decode enough of the outside and you might ruin the inside for someone else. That's a hard mirror. We like to think understanding adds options. Here, understanding can delete a landscape. So the community builds an ethic around it, even if it's unspoken. Don't pretend impossibility where difficulty lives. Don't sell difficulty as destiny. And don't forget that in quantum mechanics, asking a question is doing a thing. A microstory anchors it. A young researcher asks a senior theorist, if we can't ever see the interior, why fight about it? The answer is quiet. Because reality cares where our contradictions are. If we can move the contradiction to a place no one can reach, we're not hiding it. We're locating the edge correctly. That's not evasive. It's a method. You learn where meaning breaks by pushing until the break is the only consistent map left. Risk also looks like restraint. The page curve taught us to stop treating ignorance as a feature. Islands taught us to stop treating inside and outside as a birthright. Complexity taught us to stop treating, in principle, as a free pass. Each lesson trims a romance we wanted to keep. Each protects a deeper promise, that physics will let us be honest about what's real without pretending we can always grab it. Meanwhile, something else is happening in the way we teach this. A generation ago, we drew a black disk and said, "Beyond here, mystery." Now we draw a boundary and say, "Beyond here, a code." That shift matters for the people who will spend their 20s and 30s carrying the argument forward. Mystery is a mood. Code is a task. It invites craft, collaboration, failure you can learn from. It turns awe into work. So we circle the horizon the way climbers circle a cornice, testing, probing, learning its smell in different weather. We accept that one wrong step collapses the surface you trusted. We also accept that the only way to map the safe line is to inch along it. That's what the firewall debate has done, laid a rope along a ridge where meaning and measurement separate. The rope holds because enough hands hold it. That's science as a human practice, not a slogan. Resolution and broader meaning. In the end, the universe defends its secrets with boundaries, some drawn by principle, some by time, and our job is to find exactly where they run. If you want to follow this edge to its next cliff, watch our deep dive on how entanglement builds space, equals Epper in practice. Subscribe to stay with the story as we test the horizon's whisper with sharper ears, and bring a friend who likes maps more than myths.